Osmotic pressure is represented by the symbol pi. Osmosis, basically, let us take a solvent in a beaker and try to keep one glass tube. So here, this is solvent or low concentrated solution. This is a solution or high concentrated solution. Here it is a semi-permeable membrane. So first of all, let us discuss about the semi-permeable membrane, then we shall back to the what is osmosis and osmotic pressure. So I am taking the semi-permeable membrane. So what is semi-permeable membrane? Semi-permeable membrane is a thin layer that allows only solvent molecules to pass through it, but not the solute molecules. Whatever the type of solute molecules it may be. So the porous size of the this semi-permeable membrane is very small, so that it allows only solvent molecules and cannot allow the solute molecules. So allows only solvent molecules, but not solute molecules. Such type of thin layer is known as the semi-permeable membrane. Let us see what are acting as the semi-permeable membranes. So we can take the plasma membrane, which acts as semi-permeable membrane. Cellophane paper, acts as semi-permeable membrane. Calcium phosphate, Ca3PO4 taken twice. If this is applied on a paper, it also makes the normal paper as the semi-permeable membrane. Pig's bladder also acts as semi-permeable membrane. Cellulose acetate, semi-permeable membrane. Next, cupric ferrocyanide, Cu2 FeCN taken 6. So these are all acting as the semi-permeable membrane. Let us see a small application of the semi-permeable membrane. Imagine there is two solutions. So in between there is a semi-permeable membrane. So one side we have taken 0.1 m AgNO3 solution. The other side, let us take the 0.01 m NaCl solution. The question is, when AgNO3 reacts with NaCl, it forms a white precipitate of AgCl. White precipitate is formed. So whenever AgNO3 and NaCl solutions are separated by the semi-permeable membrane, the question is, in which side the white precipitate of AgCl is formed? Whether on the side of the AgNO3 or on the side of NaCl, or both sides it forms, or no side it forms. Actually, since semi-permeable membrane do not allow the movement of the solute molecules, that's why AgNO3 and NaCl cannot cross the semi-permeable membrane to react. So no reaction occurs, hence there is no precipitate formation on both the sides. So this is the application of the semi-permeable membrane where we can see that. Now let's come to the osmosis process. Whenever a solution or solvent or higher concentrated solution and lower concentrated solution are separated by the semi-permeable membrane, let us imagine this is an open container. We know that lower concentrated solutions or solvent has the higher vapor pressure. The pressure on the solvent is higher than the solution. Solution also creates some vapor pressure. Let's imagine this is the vapor pressure of the solvent and this is the vapor pressure of the solution. We know that always at a given temperature, vapor pressure of the solvent is greater than the vapor pressure of the solution. So vapor pressure is always acting as unit area. So the pressure exerted on the solvent side is more and the pressure exerted on the solution side is more. So there is an imbalance between the pressures. So automatically, since more pressure is applied on the solvent side, so it activates the solvent molecules to enter into the solution side. This is the solvent molecules present in this solution do not enter this side. Why? Because the solution is feeling the less vapor pressure. Solvent is feeling the more vapor pressure. So automatically, spontaneous movement of solvent molecules from solvent to the solution is observed. So the spontaneous movement of solvent molecules from solvent to the solution or low concentrated solution to the higher concentrated solution through the semi-permeable membrane is known as the osmosis process. Let's imagine initially the level of the solution is up to here, this particular point. Because of the difference in the vapor pressures of these both liquids, the osmosis continuously takes place, which makes more amount of the solvent to enter into the solution. As a result, the concentration of the solution decreases and the level of the solution increases. This level of the solution is increased because extra amount of the water, here I am taking the water, extra amount of the solvent or water molecules are entering into the solution side. Because of the extra amount of the solvent developed on the solution, that solvent develops some pressure on its own liquid because of the increase in the level. So the pressure developed by the extra amount of the solvent molecules entering into the solution is known as hydrostatic pressure. And this hydrostatic pressure slowly opposes the movement of the solvent molecules into the solution. That means slowly it is opposing the osmosis process, and it cannot oppose instantaneously and initially. Why? Because that hydrostatic pressure is not sufficient to stop this pressure coming solvent molecules because of the higher vapor pressure. And once the sufficient amount of the liquid is developed and pressure is also developed, so at a particular point, this hydrostatic pressure is sufficiently developed and opposes the movement of the solvent molecules into the solution. So that movement, osmosis, shall be stopped. So that pressure, whatever the extra pressure that is developed on the solution to stop the osmosis is known as the osmotic pressure. So here, osmotic pressure is nothing but the hydrostatic pressure that is extra developed, which is equal to the oppose the osmosis process is known as the osmotic pressure. And without hydrostatic pressure also we can see the concept that if you mechanically applying the pressure, if that pressure is able to stop the osmosis, that pressure is also known as the osmotic pressure. So the pressure to be applied on the solution only just to stop the osmosis is known as the osmotic pressure. Osmotic pressure is denoted by the symbol pi. The question is, what happens if higher pressure you applied? So more than the osmotic pressure if you apply, imagine here osmotic pressure I am taking it as a 1.2 atmospheres. So 1.2 atmospheres is sufficient to stop the osmosis. If more than this 1.2 atmospheres pressure is applied, then that extra pressure will influence the solvent molecules from the solution to enter back into the solvent molecule. That is what called the reverse osmosis. So reverse osmosis is, in the reverse osmosis, solvent molecules are flowing from the solution to the solvent because of the extra amount of the pressure added. Now, let us see here osmotic pressure. What happens if the difference of the concentration between the solvent and solution or low concentrated solution and higher concentrated solution increases? Higher the concentration of the solution you have taken, lower shall be the vapor pressure, that is, it is developing. So difference in the vapor pressures increases, so that rate of osmosis increases, so that more level of the water or a solvent increase, so the hydrostatic pressure also increases. that means osmotic pressure also increase, or else you need to apply the higher vapor or higher pressure to stop this flow of the solvent molecules. So when the concentration increase, automatically when the concentration difference increase, osmotic pressure also increase because osmosis increase. So that's the reason why we can write down that pi is directly proportional to the concentration. So in this case, practically it was proved that pi is equals to CRT, where C stands for the concentration in molarity. So I can take that pi equals to MRT, molarity. And molarity means we know that molarity equals to number of moles of solute by volume of solution per liter. So if by substituting that value here, we can get the pi equals number of solute by volume of solution in liters into R into T, or else we can write down pi V equals to N2RT. Now by elaborating this molarity, we can write down that pi equals to, molarity means weight of solute by molecular weight of solute into 1000 divided by volume of solution milliliters into R and T. You can calculate the osmotic pressure using like this given information. Then what are the temperature? T stands for temperature in Kelvin, R means universal gas constant, pi is the osmotic pressure. So the values of R should depend on the units of the pi what we are taking. For example, if pi value is taken in the atmospheres, then R value should be equals to 0.0821 liter atmospheres per Kelvin per mole. If pi value is taken in the bar, then R value equals to 0.0831 liter bar per Kelvin per mole. If pi value is taken in the millimeters of Hg, then R value equals to 62.4 liters per Kelvin per mole. If pi value is taken in the pascals, then R value should be in the SI units 8.314 joules per Kelvin per mole. So like this, based on the units of the osmotic pressure, where we are going to calculate, the R value has to be selected. Now, let us see here. What happens if two different solutions having same solute but different osmotic pressure are mixed? Then here, when two different solutions with same solute and different osmotic pressure, different pi values are mixed, then how to calculate the osmotic pressure of the resultant solution? That is nothing but pi value is equals to resultant solution is equals to pi 1 V1 plus pi 2 V2 divided by V1 plus V2. By adding like this, we can calculate the resultant solution osmotic pressure, where pi 1 stands for the osmotic pressure of the first solution and its volume in liters, and this is the second solution osmotic pressure and volume in the liters. V1 plus V2 is the volume in the liters. If you take the volumes in the milliliters, here also we can take the volume in the milliliters. Now, what happens if different solutions with a different solute, not same solute now, solute is different, are mixed, then the resultant solution osmotic pressure pi R is equals to pi 1 plus pi 2, or else we can write down that pi R equals to N1 I1 divided by V1 plus V2 into RT plus N2 I2 by V1 plus V2 into RT, or else we can write down final form as pi R equals to N1 I1 plus N2 I2 divided by V1 plus V2 into RT, where I stands for the Van 't Hoff factor that we shall discuss in the coming classes. Now, coming to the reverse osmosis process that we discussed already, when higher osmotic pressure, more pressure is applied on the solution which is more than the osmotic pressure, solvent molecule starts flowing from the solution to the solvent. That is what called the reverse osmosis. So by using this reverse osmosis, seawater is purified. That process is known as the desalination of the water. D stands for the removal. Saline means salt. Removal of the salt happens. So let us take this seawater in this side and normal water other side, and here cellulose estate as a semi-permeable membrane, let us use it. And when higher pressures on the solution is applied, automatically the water molecules present in the seawater start flowing into the solvent molecule, so that salt remains there only, that can be removed later, and whatever the water is coming out, that can be used for the other regular purposes. That is what called the desalination of the water. Now let us see what other type of solutions are there regarding the osmotic pressure. So let us discuss about the isotonic solutions. Solutions having same osmotic pressure are known as isotonic solutions. Means the osmotic pressure of this solution, osmotic pressure of this compound mixture solution, if both are same, then since both sides same osmotic pressure is there, so that no movement of the solvent molecules are observed. So when isotonic solutions are separated by the semi-permeable membrane, no osmosis takes place. That means osmotic pressure of the first solution is equals to the osmotic pressure of the second solution. Then in such cases, their C1 RT is equals to C2 RT. If R values are always constant, so that we can cancel it. Even if temperature is also constant, we can cancel that, so that we can write down C1 is equals to C2. Here C stands for the molarity. Molarity means number of moles of the solution, solute by volume of the solution in the liters, is equals to N2 by volume of the solution in the liters. So if the equal volumes are taken, then volumes can be cancelled out. If equal volumes are not taken, then this formula is applicable. And for equal volumes of solutions, so volumes cancel out, so that we can write down the number of moles of the solute of the first compound equals to number of moles of the solute of the second compound. So number of moles means, again formula is weight of solute by molecular weight of the solute of the first combination is equals to weight of the solute by molecular weight of the solute of the second combination. So by knowing this, we can calculate the molecular masses and mass of the respective solutes present in the different solutions. That is about the isotonic solutions. Let us see, is there any isotonic solution? Means yes, there is an isotonic solution. We can take that 0.9% weight by volume NaCl solution has, it is isotonic with the blood. Means the blood osmotic pressure and 0.9% weight by volume NaCl solution osmotic pressure are same. What happens if osmotic pressures are different? Now let us see here. Imagine, let us try to place a blood cell in a solution, NaCl solution here. So this NaCl solution concentration is 0.9% weight by volume NaCl solution I am taking. Since osmotic pressure of the solution and osmotic pressure of the fluid that is present in the blood cell are same, osmotic pressures are same, then no osmosis takes place either to inside or to the outside. So the size of the blood cell remains same and it is not affected. And second case, what happens if higher concentrated solution is placed, 0.9% weight by volume NaCl solution is placed. That means now blood cell is placed in the higher concentrated solution. So this concentrated solution is higher and this concentration of the solution is less. Then automatically osmosis takes place from the blood cell to the outside. That means lower concentration to the higher concentration, the solvent molecules like water molecules starts flow out, so that the size of the blood cell decrease. That means it shrinks. So that disease is known as the plasmolysis. Now, let us take what happens if the blood cell is placed in the less concentrated solution than the 0.9% weight by volume NaCl solution. So now outside concentration is less and inside concentration is more, then automatically solvent molecules start flowing from the lower concentration to the higher concentration. Then the size of the blood cell increases, that means it swells. And after some time it may burst also. So that is called as the haemolysis. So here we have taken the three different type of the solutions. The solutions which are having the equal concentrations automatically will have the same osmotic pressure. So they are known as the isotonic solutions. Now here the concentration of this solution is less. Here we have taken the higher concentrated solution. So the solution in which higher concentration is present and such solutions also having the higher osmotic pressure. Such solutions are known as the hypertonic solutions. The solutions which are having the higher osmotic pressure are known as the hypertonic solutions, and we said that pi is directly proportional to concentration. So when concentration increases, osmotic pressure also increases. So when a blood cell is placed in the hypertonic solution, it shrinks. And a hypotonic solution, the solutions for which osmotic pressure is less are known as the hypotonic solutions. Usually when the concentration is less, osmotic pressure is also less. Such solutions are known as the hypotonic solutions. So when a blood cell is placed in the hypotonic solution, so it swells up because the concentration of the solution is less. So solvent molecules start entering into the blood cell. Apart from this, what are the other applications of the osmotic pressure? Usually osmotic pressure is used in the calculation of molecular masses of polymers which are insoluble in water. Next, biomolecules like proteins. Usually that means basically macromolecules. Together we can call them as a macromolecules. So osmotic pressure is used to calculate the molecular masses of the macromolecules like polymers and the proteins. And osmotic pressure is the better method to calculate the molecular masses of such type of the molecules compared to the boiling, elevation boiling point and depression freezing point. The reason is, in the elevation of boiling point, we have to take the solution till its boiling point. Then only we can calculate the how much elevation of boiling point is there. And in such cases, biomolecules like proteins are unstable at the higher temperatures and they may decompose. So that's why the elevation of boiling point is not suggested. And depression freezing point, so that you have to take the solution till the lowest temperature till it freezes out. And that is also not correct for the proteins. Again, they may dissociate or they may decompose completely. And polymers are completely insoluble in the water, so that both elevation of boiling point, depression of freezing point cannot be observed. So that is the reason why if you take the osmosis and osmotic pressure concept, And osmotic pressure means here we are not increasing temperature, because osmotic pressure can be measured even at the room temperature also. So that is the reason why there is no change in the molecular formulas of these chemical components. And one more thing is osmotic pressure magnitude. Even for the smaller concentrations, you can easily observe the pi calculation. Osmotic pressure can be calculated. And in the elevation of boiling point, depression freezing point, we are using the molality, which is independent of the temperature. And in this case, we are using the molarity, so that volume changes, even for small volume change, osmotic pressure can be calculated very easily. So for there, we are using the osmotic pressure. And then osmosis, where we can see the osmosis in our regular life. Raw mango pickle preparation. So whenever raw mangoes are cut and they are having some moisture, so that moisture has to be taken out first. So for that one, they are using the large quantity of the salt solution. So when salt is added, salt is highly concentrated one, because of the osmosis, because solvent molecules now flows from the raw mango pickles cells into the higher concentrated salt solution, so that all water will come out, and finally the raw mango pieces become shrivel, and they shall be used for the preparation of the pickle later. At the same time, wilted flowers, whichever the flowers are wilted position, so by adding the water, so that they revive again, they come to their original position. And carrot limbs also in the vegetable shops, we can see that by adding the fresh water, again they revive to their original tighten position, and they firm once again. And other places where we can see is, particularly in the preservation of the meat, we add the salt, because the salt concentration will take out the bacteria or other microorganisms blood fluids out, so that the microorganisms shrivel and they will finally die. And also in the storage of the fruits, there we are using the sugars. When sugar is sprayed over the fruits, so this sugar also is a highly concentrated solution, which will take the blood fluids of the those microorganisms, and they will die. So there we can use the preservation of both of these. So dear students, I hope you understand this osmosis and osmotic pressure, and we shall meet in the next class. Thank you, one and all.